Building on from the ideas of quadratic expressions, quadratic equations, and solving quadratic equations, we're now going to look at our first nonlinear function, the quadratic function. We'll also be looking at its graph. In a quadratic function, the dependent variable is a variable that's calculated using a quadratic relationship or expression. So for example, with x as our independent variable and y as our dependent variable, we'd have something like this: y equal to a function of x, where that function is a times x squared plus b times x plus c. And a, b, and c are just constants given in the definition of that function. Quadratic functions like this are nonlinear, and their graphs are also not straight lines. In fact, the graph of a quadratic function is a curve called a parabola, which you may have heard of before. Parabolas are somewhat well described as being U-shaped curves, or possibly upside down U-shaped curves. As with linear functions, we can sketch the graph of a quadratic by joining a bunch of coordinates with a smooth curve. Alternatively, we can get a better picture of it by using 4 key characteristics of the function. And here they are. Plotting the graph of the function can be done by following these steps. First of all, we find and plot the x-intercepts, that is, the values of x at which the function value is 0. This is done by solving the quadratic itself, so we need to know how to solve quadratic equations. Something to keep in mind though is that if b squared minus 4ac, the discriminant, is less than 0, there are no real solutions to the quadratic, and this implies that there are no x-intercepts for the graph of that quadratic, although it can still be graphically drawn in the real Cartesian plane. After the x-intercepts, we find and plot the y-intercept. It's a fair bit easier and is found by setting x equal to 0, and we find, of course, that y is equal to c, the constant at the end of the quadratic. Third, we find and plot the turning point of the function, remembering that the quadratic is a U-shaped kind of curve. It has a turning point at some stage. This always occurs at an x value of minus b on 2a. The corresponding function value is found by simply substituting this value for x back into the function, or as we write here, f of x turning point. Finally, we need to use the concavity of the function to join the above coordinates with a smooth parabolic curve. This means that when a is greater than 0, the graph is a smiley shape, or opens upwards. On the other hand, if a is less than 0, the graph has a frown shape, or opens downwards. Let's try it out with these 3 example quadratic functions. I've copied down the 4 points that we need to follow in order to find the graph of the quadratic functions. Just pasted it up here on the right. In the first example, f of x is equal to x squared minus 5x. First thing we need to do is find and plot the x-intercepts by solving the quadratic part. So we set 0 equal to x squared minus 5x, which we can factor to find x outside of x minus 5 is equal to 0. And this implies that x is equal to 0 or x is equal to 5 will be our x-intercept. Next, we need to find and plot the y-intercept. The y-intercept is just the c value, or the constant from the quadratic. Here there is no c, there is no constant term, only an x squared and an x term. So our y-intercept is going to be equal to y equal to 0. Third, we find and plot the turning point of the function. The x value for the turning point is going to be minus b on 2a. Here b is minus 5, so we're going to have 5 over 2 times a, which is 1, or 2. So x turning point is 5 on 2. To go with that, we need the function value. We substitute the x value back into the function, and we find that we get 25 on 4, take away 25 on 2, which we can evaluate to give minus 25 on 4. Finally, for the concavity of this function, we look at the a value, the coefficient of x squared. Here a is equal to 1, and 1 is positive, 1 is greater than 0. So looking up here, we note that when a is greater than 0, the graph will open upwards, so we should have this kind of shape. Now we can go ahead and put all this information together on the Cartesian plane and join our dots with a nice smooth parabolic curve. To save a little time, I've set this one up. So we've got the f of x-axis, the x-axis, the two purple points are the x-intercepts, the orange point sitting on top of that one is the y-intercept, and down here we have the turning point at 5 on 2 minus 25 on 4. The last thing I have left to do is join them somehow with a parabolic curve with this open up shape. Now of course it is going to be a little bit approximate and it may look a little bit sketchy, but that's okay, we are just sketching. So we need something that looks kind of like this. And I'm just going to label that as well. It's quite okay if you wanted to put y here for your axis too, that's fine. Anyway, so there's our first quadratic function graph. Give yourself some time now and try it out for B and C. In B, we have f of x equal to x squared plus 2x minus 3. First of all, we look for the x-intercepts by solving x squared plus 2x minus 3 equal to 0. You can factor this one and you'll find that x is equal to 1 and x is equal to minus 3. For the y-intercept, we pull off the constant, y equal to minus 3. The turning point, x value is given by minus b over 2a, which gives us minus 1. Evaluating the function at minus 1 says that the function value corresponding to the turning point is going to be minus 4. And finally, a is positive, it's a 1, so we're going to have the open upwards U shape. Okay, so I've given myself a little bit of room to show this one a bit better. I'm using the same colors for my key points. So I've got the turning point here in green, y-intercept, and the x-intercepts in purple. Again, remember we're opening upwards with this parabolic curve, and it needs to turn here at minus 4, coming up through the orange point, up through the purple, and then mirroring that on the other side. A good point to note is actually helping you when you're drawing these is that the graph should mirror across that vertical line through the turning point. And mine's roughly there, I think, with that one. The third example we have is f of x equal to x squared minus 8x plus 16. I'm going to leave some of the detail to you here, but first of all we have the x-intercept. You'll find that when you solve the quadratic you only get one value for the solution here. It's x equal to 4. The y-intercept, again, you can read off, is y equals 16. The turning point, minus b over 2a, is going to give us 4, and the function value there is 0. And finally, a is equal to 1, which is greater than 0, so we have an opening upwards shape. Now the problem with this information is that we're down a little bit in our first piece of information. We've only got one x-intercept. Now that's not a big problem because we can use the information I just gave you up here that the graph is symmetrical about the turning point. We can use that to generate an extra point to help us out. I'll show you that in a moment. Okay, so here's my graph setup. You'll notice most of the action here is going to occur in the positive quadrant. So I've put my x-intercept down here, the purple dot, the y-intercept in orange. Now again we're complicating things because the turning point is exactly the same as the x-intercept, so there it is sitting on top. We've only got 2 points here to tell us what to do. Well, remembering that our graph needs to be symmetrical about the turning point, this orange point should be mirrored across to the right of our symmetry line. So I notice that it's 4 across to the left of my turning point, so I look 4 to the right and then move up to the same line as where I've got 16 over on the left. So now I've got at least 3 points that I can work with. If you're uncomfortable with filling in the dots from here, remembering that it's only a sketch, you can go ahead and just evaluate the function for some different x values. For example, when x is equal to 2, we get 2 squared is 4, minus 16 is minus 12, plus 16 is 4. So we get a new point here. Again, we could mirror that across. And we're starting to get a nice picture. Once we're at that point though, we can start to fill in the detail. So we start to sketch our curve, passing through the points that we've got. And there we have it. There's our f of x curve for x squared minus 8x plus 16. Okay, so in this video we've introduced the idea that we can have a function comprised of a quadratic, our first nonlinear function. We saw that there are 4 key characteristics of these functions that can help us to graph them. And we've graphed a number of different examples and tried to deal with some issues when our 4 key characteristics failed us a little.